I am currently the chief engineer for industrialization at GE Aviation, and it's really a role that evolved out of GE's interest in vertically integrating complex new materials and their introduction into products. It's an important role in the context of integrating the different aspects of CNC. So, for example, you need to be able to design with an entirely new material. And we have some fabulous designers who are uh, figuring out how to use the capabilities of these new materials. Materials engineers capable of understanding and delivering on the specifications that we have for these materials. And then, of course, manufacturing these materials at scale. A lot of my expertise over the years has been in two major areas. One is how do you translate innovations from the lab or from early stages of invention all the way into product and production. And a specific aspect of that is the scale up of these materials. And scaling up of the ceramic composites has been, a great experience, great learning, and we have learned a lot. So I think that is a very broad question, and there's a lot of information from GE out there, including from our CEO talking about it. I will address it in the context of this technology, which really, if you think about it, is aimed at increasing the temperature of operation of the engine. If you historically look at it, for every decade or so, metals typically moved up about 50 degrees in temperature capability. And the hotter you can fly an engine, thermodynamics will tell you that the more the engine is efficient, its performance goes up and you consume less fuel. The ceramic matrix composites give you a tremendous jump in capability of hundreds of degrees of temperature, and that obviously improves fuel efficiency quite a bit. It's also much lighter than metal, and so that gives you an additional benefit beyond just the capability of temperature. GE is, of course, working on other technologies like hybrid electric vehicles and so forth, which contribute to sustainability. And like I said, there's a lot of information about GE's contribution in this area in the open literature, which you can look up. Yeah, it's an interesting question. So there are two aspects of it that I want to address. First of all, I think digitization, in many ways, people think about as something new in the field, and that's obviously not true, because data has always been integral to the way both the aerospace industry and the ceramic industry always operated. What has really probably changed is the amount of data that one can get both during flight and during the production process. And I'll specifically address the production process. Today, in the production of advanced materials, including composites, one can get a very large amount of data on many aspects of the production and the stability of the controls and so forth. And so using the data to create the right kind of information, looking at patterns and sort of looking for leading indicators, which can tell you ahead of something, what are the trends emerging in production, are some raw material inputs leading to some effects and so forth. That's, I think, one major thing that we have learned from digitization. The second major aspect of digitization is, of course, the amount of information that is coming from the field as the engines fly around the world. And you can now get information on the performance of the product much earlier from the field, very directly, analyze it, understand it, so you can help the customers keep the engines flying more efficiently in the sky. So those are two key aspects of digitization that has helped us a lot. The third aspect, of course, which is more common, is the impact of digitization on the way we design materials or design products, right? You can now simulate a lot of conditions which needed to be done experimentally. Now you can simulate them, see the effects, look at different boundary conditions. And it's interesting to see a whole generation of engineers get trained in college on computer skills that they can now use to figure out whether the performance of a product or material will satisfy customer requirements, and do this based on simulating the key requirements, so that you don't need to run all the different combinations of experiments that one would have traditionally done. I think there are different ways one could think about it. In the very short term, one could think about the pandemic as affecting flight, and obviously that has slowed down some of the amount of engines sold or service, but that is coming back. I think that's a temporary change in the industry. It's a big impact, but there is a lot of information out there again in the public domain about the impact on the industry and how the industry is doing with it. At a broader level, I think the key question is, how do you take a niche product like ceramics or ceramic composites and help it proliferate the marketplace? What are the other opportunities for ceramic materials? And I think that'll be an important question to address in this conference, is asking the question, not just can you make a new material, which is where a lot of the research and development effort is directed at, but ask the much broader question of, can you now scale this material into product at a price point that makes integration into the system better, right? If you don't make it at the right performance level, of course, nothing matters, right? You need to first work right. So the product needs to perform as we designed it to perform, right? And it has to be safe and all the other aspects that are critical to the aerospace industry. But if you cannot make it at scale, meaning that you can't make enough product to meet customer requirements, or if you cannot make it at cost, then it's not going to have the kind of desired penetration that we require. And so a lot of the challenges, in my opinion, of these high-tech ceramics is our ability to be able to scale and have them at the right cost while maintaining the performance at the highest level. I think that's probably the challenge that was there. We are addressing it in the current generation, as I talked about, and it's going to continue to be the challenge that we need to talk about in the future. The way I think about these shows is you are always looking for ideas that advance the state of the art. At the same time, I think it is our obligation as a large player in the industry, both as a company and at a personal level, scaling up of ceramics and scaling up of materials, translating innovations so that they have an impact on the customer. These are things close to my heart personally. So these shows are a forum for us to interact with some of the world's best minds, because it's all a team sport, right? No company, no person alone can do any of these things. You need to advance the state of the art of the industry and the state of the art of the knowledge. That occurs in universities, that occurs in national labs, that occurs in industry. And this interaction is what makes it possible. And so I look forward to meeting people from across various disciplines, across various sectors, and probably from all over the world, to be able to talk about the latest advances, learn from them, and hopefully contribute a little to the advancement of the knowledge. I always say it's one of the best things you could ever do in your career. I'm probably a little biased that way, but think about it in broader historical context, right? History has been really gated by materials. Think of the Stone Age and the Iron Age. Think of the materials that have influenced the modern age, like silicon. In many, many ways, advances in materials are what has made the world today that we live in possible. And as a materials engineer, you are able to influence the future of not just the materials that will exist in the future, but be able to do it in a way that is sustainable. Here is an example that I've always thought about. If you think about nature, nature is a very interesting material scientist. It produces materials of all shapes and forms, from polymers to ceramics, and it's able to do it in a regenerative way, right? You're able to make materials from the earth. The earth creates new new material, and then it eventually all goes back and integrates back with the earth. So if you asked a question about sustainability, but if I think about it at an even much broader scale, a lot of bio-inspired materials, which is an area that I have been interested for a long time, and we have also worked on that area, is probably an example of the integration of materials, biology, and maybe computation. As can you code the material to be able to make itself or self-assemble itself? Can we make self-repairing materials? Can we make materials that are able to sense itself, just like our skin is able to sense if there is a cut and heal itself? Are there technologies that one can think about where the material is capable of understanding that it has a particular defect in it and it's able to heal the defect and so forth? So there is a lot of exciting technologies at the intersection of, I would say, biology, materials, and computation that are coming up. That'll be fascinating for the next generation of engineers. And at the same time, for the current generation of materials, metals, and ceramics are everywhere, right? You can't build a physical world without materials. So materials, I think, are the core of success of engineering. And I encourage everybody who is considering to be an engineer to be a materials engineer, because it's a materials world.